Hi. So welcome back to the lecture series on point set topology. In the last lecture, we have discussed some topological properties of matrix spaces, and also we have introduced the basic topological concepts as well. Now let us go on with our discussion. So today we are going to talk about something called interior points and limit points. So if you remember the definition what we have discussed in when we are discussing what a matrix space is. So suppose here matrix space X comma D is a matrix space, okay? So then we defined interior point in such a way that is, there is small x belongs to capital X. This is said to be an interior point of let's say take a subset. A is subset of X. Of course it is non-empty, and we have chosen an element from capital A only because as X is a open set itself, so every point of X is an interior point. So it is better to consider a particular non-empty subset. So that's why you have chosen small x belongs to A. So X is said to be interior point of A if there exists epsilon belongs to real number larger than 0 such that B epsilon of X is exactly inside capital A. So that means if you consider this is my A, so a particular point you choose, so of course you will get certain neighborhood such that this particular ball with radius, let's say it is my epsilon and it is my X, it's completely inside capital A, okay? But when we are, if we consider X comma tau is a topological space, then we don't have this luxury to choose any particular epsilon or any kind of ball. Rather, we have the liberty to choose any open neighborhood. That means then let's say A is subset of X as well. A is non-empty. Let small a belongs to capital A. Small a is said to be interior point okay, let us take it some above, yeah, it's fine. Interior point of A if there exists UA is subset of X and UA is open neighborhood around X. That means it is an open set containing X, okay, such that then X must belongs to UA, that is because it is a neighborhood and is completely inside A. Okay, not UA, let us consider UX because it depends on the choice of small x, okay? So yeah, this is the thing. So it must contain open neighborhood around this. That means if you consider A can be written as union of all small x belongs to X UX. I mean interior of A, sorry, the set of interior of A. So that means the interior of A means it is a set of all interior points. So interior of A, this is open set. Now you find that it is an analogous version of what we studied in case of matrix spaces, right? All right. So that is, so this basically, so once we have A is open set, A is open means the entire union small x belongs to capital X UX, this will be same as A itself. In fact, when we have A is open set, then for every X belongs to A, we can choose ux to be a itself. Okay, so there is a proposition that implies this above result. So this says that suppose x comma suppose a subset of x, where x is a topological space, is open if and only if a is equal to interior of a. Means every small a belongs to a, small a is an interior point of a. Okay, that means if you have this a, you can cover this a with such open balls. All these small open balls can cover the entire A. Okay, this is how one can cover the entire A. So this is explicit definition or pictorial representation of an open set. Alright, so for example, so suppose we have set of all real numbers with normal Euclidean topology, then every let's say a comma b such that a is strictly less than b. So these are open set, right? So you can take an exercise to prove it. Later we will see that these are called the basic open sets. Okay. Now let us see a very beautiful evidence. Let us consider R comma tau. It is normal Euclidean topology. Okay, it's a normal Euclidean topological space. So we consider, and also R comma tau L, this is the lower limit topology. So lower limit topology means where the open sets are of the form A comma B, or union or some intersection, or arbitrary union of these sets, or finite intersection of these kind of sets. I mean arbitrary union of these sets, that's fine only. So these are the basic open set. We'll define what is basic open set, but for now just consider that any open set will be any arbitrary union of this kind of set. Okay, so alright, now we consider A to be 0, 1. So first of all, what are the properties that one can quickly figure out? That this is not open set, this is not closed set. First of all, these two things are there. So why it is not open set? So it is not open set because you can easily see that 0 is not interior point. Why it is not closed set? Because 1 is not interior point of a closure, because once you take a complement, better to write it as R minus A, because there may be some rotational ambiguity. Once you consider r minus a, it will be nothing but minus infinity comma 0 union with 1 comma infinity. So 1 is not a interior point. Okay. Basically it is a this, so up to here and 1 up to here, this region and this region. So if you take any one is there, so whatever neighborhood you choose, this particular region will be outside of this set. Similarly here as well, if you consider, let's say 0 1, if you consider any neighbor around 0, it will be this particular portion will be outside of the set. Okay. So that means in lower limit, in normal Euclidean topology, this set is not open. But once you are in lower limit topology, so in case of lower limit topology, so then 0 comma 1, this is open set. So 0 is interior point. Okay, so this is the very beautiful evidence that if you because once you have any particular set, you see that the set is fixed, underlying set is fixed, it is set of all real numbers. But once you change the topology, a particular set may change its property. Okay. Now, what is the limit point? So, limit point is basically just it have some different configuration or always a different property. So, this says that suppose x comma 2 is a topological space. Okay, so if it is a topological space, then let's say A is subset of X, and of course A is non-empty. So every time I'm not bothered about empty set, because empty sets are usually by vacuous condition it is open as well as closed. So that's why we, in the definition of topology, we have considered the entire full set and empty set to be closed and open as well. So that's why I'm just bothered about the non-empty sets as well. So that's why suppose you consider A is subset of X, which is non-empty. Let us consider small x belongs to X. This is a point and this is said to be limit point of A if for every open neighborhood U A is subset of X, U A minus singleton A intersection with A U A minus not UX, it is UX. UX minus singleton X intersection with 8 is non-empty. That means suppose we have this set A, we are taking any point, if it is outside of small x, then this portion is not it can be resolved in UX intersection A, because once x is outside of A, so there is no need to delete small x from the open set. So that means if you take any open set around this, it must intersect with A. That means this particular intersection has to be non-empty. So that basically implies that this intersection, UX intersection A, this must contain one element y such that y is not equal to x. Okay, so this contains at least one point which is different from x. So that is the definition of limit point. That now if you consider, suppose you have a sequence, let's say 1 by n, natural number. So this, what is the limit point of this set? So this limit point of the set is 0. In fact 1 by n is converging at 0. So once you have a sequence and consider a particular the collection as a members of that particular sequence, then of course the point of convergence will be the limit point of that particular set. So that means if you consider any neighborhood around 0, then it must contain one element of from the particular sequence. That's the same definition here, that it must contain one element which is different from that particular point small x. Alright, but why it is important? So with this property we can characterize whether a set is a closed set or not. So suppose x comma tau is a topological space. Let's say A is subset of x and A contains all of it limit points, then A must be closed. So why it is closed? Just to say, if you want to show that it is closed, for example, suppose a subset of x, this contains limit points. So now if you consider a closure, for example, suppose consider this is my x and this is my A. So suppose you consider one element from A closure, sorry, x minus A. So here is my small point, let's say, let's give this name as small x. So we have to show that x minus A is open, right? So once you have x minus A is open, so x is not in A first of all. So you see that x doesn't belongs to A. So that means x is not a limit point. So that means there exists one UA, one UX, one neighborhood UX such that UX minus singleton x. Now you see that x is not in capital A, so that means this particular thing is not needed. So UX intersection A is completely free. So that means UX is subset of A complete, x minus A, complement of A. So this UX is completely inside x minus. So that means x minus A, this is open set. So I can write x minus A to be as union of small x belongs to x minus A UX. But what about the converse? Converse means is that suppose suppose A is closed. Okay, so let us consider small x is one element from small x is a limit point. So let small x is limit point of A, and small x belongs to x minus A. So as small x belongs to x minus A, so that means small then x minus A is open set, right? Because A is closed set. You have assumed that X is closed set. So that means there exists one neighborhood which is completely inside UX. So it is UX. Okay, okay, not for that. So let us consider UX to be as x minus A. Now UX intersection with A must be non-empty. This must contain one element from small a. That means small y belongs to A intersection with x minus a. But that is not possible. Not possible. Because a set will be always distant from its complement, right? So that means small x must belongs to A. Hence A contains midpoints. Okay. So now, as we have we can define all the interior points. We can name the collection of our interior points as the interior of A. So similarly, there is also something called closure of a set. So what is a closure? Suppose A is subset of X. So A closure denoted as this A bar, it is A union the limit points of A. So the collection of limit points is basically denoted as D of A, and this is said to be derived set of A. Okay. So this is a closed set obviously, because you can see that A closure, x minus A closure equal to x minus A intersection with x minus limit points of A. So that will be always a closed set, open set. Okay. So this A closure is a closed set, and not only that, A contains A closure. So A closure is a closed set that contains A. Now if we consider that, now suppose A is a set, so A can be inside some more other closed sets. So what is the relation between, what is the speciality with A closure? So A closure, this is the smallest closed subset of A. So how can I prove it? So there is a proposition that says that suppose x comma tau is a topological space, then A closure equal to intersection of all Z, it is closed set, and Z contains set. Intersection of all the closed subsets that contains set. It's an exercise, you can check it by your own. Okay. Okay. So we have defined some analogous statements in interior points and limit points as well. So it's a very short lecture. So just let me just stop it here, and in the next lecture onwards, we'll start with continuous functions and Hausdorff spaces. I have just I could cover up the continuity here, but I want you to brush up all the previous concepts, because from next lecture onwards we'll rush. There will be a huge rush, because later in quotient topology, Grassmannian bundles, everything will be covered, but there you won't get any time to recall the previous concepts. Okay, so with this short lecture, I'm just giving you a home task to try to solve the exercises from Kumaresian metric space and topology of metric space, sorry, metric space. Okay, so just try it. In the next lecture we'll be thoroughly study what is continuous functions, and because that is going to be very, very important in study of later algebraic topology, and in fact in algebraic geometry everywhere. Wherever you will learn, you want to go, everywhere it will be important. Alright, so just call it a day. Thank you very much.